Very good morning, children. How are you all? Yeah, very nice. In this video, we are going to start a new chapter that is called as the equilibrium. Right? In this equilibrium chapter, we will learn many topics which are very useful for the objective level also. For that, we need to start the chapter from the easiest method that you can easily follow. So let us take here one small and simple example. Then we can write this definition after understanding that example. But don't write this definition in the initial stages. Just to save our time, we are writing all the definitions on the board to make our work simple. Done. Well, now what is meant by the word equilibrium? See, when we are taking the oxygen gas, the protein hemoglobin, it is transferring it to the lungs. It's carrying the lungs are carrying this oxygen through the protein hemoglobin to the particular organs. We know this from the biology. If at all this pumping or the transfer of oxygen is not sufficient, we say it is having an insufficient supply of oxygen. Then how do the person will be? He will be like a restless, or we say he is in deficient of oxygen. Now we say they are not a sufficient level of oxygen in his body or insufficient amount. The insufficient amount, what we are calling here, it is not in an equilibrium state. What I am calling this one as that it is not in an equilibrium state, insufficient. But when the work goes on, as usually, means enough oxygen supply is there, we say the body is under equilibrium. The body is under equilibrium. So let us take one simple example, then we can apply to our definition. Good. Now imagine we got one container. What do we got, children? We got one container. Here I am taking my rubber. Rough I am using here. I am taking a small container. In this container, there is some water. What is the children? Water is there. And I am closing this container with a lid. I am closing this container with a lid. And I started heating this water. What had I started, children? Heating this water. When we go on heating, what will happen? The liquid water will change into gaseous vapor. Liquid water is changing into gaseous vapor. Now can I just say in my reaction starting we had water and ending also we had water, but their states are different. Here during a reaction, our chemical reaction, generally what do we know? Reactants will be converted into products. That's what we know. During a chemical reaction, reactants will be converted into products. What are our reactants in this reaction? Our reactants are water that are in the liquid state and they are converted into water that is in the gaseous state. What is the process do you call in conversion of liquid water to gaseous water? In conversion of liquid water to gaseous water, what do you call? Evaporation. Do we call it as the evaporation, children? Yes. Some particles that went into the gaseous state, when they are just moving in all directions, they may come and touch again the surface of the liquid water. Generally, liquids have very less temperature than the gaseous state, we know. So here at a time when the gas giant particle is touching the surface of the liquid, now another process is also taking place. The another process that is happening here we call as the condensation. What is condensation? The gaseous particles that are touching at the surface of the liquid, they are now converting into liquid water. They are converting into liquid water. Means some of the gaseous particles are now converting back into the liquid water through the process of condensation. Through the process of condensation. Is it not, children? Yes, very good. By this, what do we can understand? When at this moment you observe the amount of liquid water that is changing in gaseous state is equal to the amount of gaseous particles that are converting into liquid state. Means we don't find any new particles. What do we observe means the amount of liquid particles that are changing into gaseous particles are equal to the amount of the gaseous particles that are changing into the liquid state. Such kind of state at which we will not find any difference in the reaction means the rate of the changing of the reactant into product and the conversion of the product back into the reactant when it goes on at a time means whenever there is no change we call the system is at the equilibrium. What is the system is said to be at the equilibrium? It is represented as a double-headed arrow. One is indicating the forward reaction and one is indicating the backward reaction. Now we will call the system as a dynamic equilibrium. How do we call the system is at the dynamic equilibrium? Let's write down the definition children. Now what we got on the board? At equilibrium there is no change in concentration of reactants and products in the reaction mixture. Means what? The number of reactants converting from liquid state to gaseous state are equal to the number of gaseous particles that are converting into the liquid particles. And the reaction continues in both forward and backward. Both forward and backward with the same rate, means with the same speed. So the chemical equilibrium is said to be a dynamic equilibrium. What is the equilibrium called now as that? It is called as the dynamic equilibrium. When it will be considered? It will be considered when the rate of the forward reaction is equal to the rate of the backward reaction. Or we speak when there is no change in concentration with reactants and products in the reaction mixture. Both will happen at a time. We call it as a dynamic equilibrium. Write down the definition children. Now we will see about the dynamic equilibrium in detail about the concept now. So let us see here now about the classification of this equilibrium. Our equilibrium is majorly classified into two types. One we call as a chemical equilibrium, second one we call as the ionic equilibrium. But before we enter into the chemical equilibrium, once we need to have a glance regarding something about the physical equilibrium. What are we studying about the physical equilibrium? Means this equilibrium depends upon the physical state of the matter. Physical state of the matter. Or we also call this physical equilibrium as the phase transformations. How do we call this physical equilibrium, children? We call the physical equilibrium as phase transformations. Phase transformations. So let us study here about something regarding this physical equilibrium. Physical equilibrium. Imagine you got a flask, thermoflask. You write no, right? Thermoflask. A thermoflask. A thermoflask. What do this thermoflask will do? It will not let any change in heat from the system to the surroundings. From the system to the surroundings. Imagine in this thermoflask we got some ice cubes. We got some ice cubes. What did we got, children? Ice cubes. Ice cubes. So before you close the lid, let us imagine some of them went into some liquid state. Some of them went into some liquid state. So here there is the liquid water. There is the liquid water, and also there is the solid water. What forms do we have, children? We have the solid water and also we have the liquid water. Let us imagine this is a closed container. This is the closed thermoflask. In this, what you are observing, the solids starts melting. The solid ice cube starts melting. See, it is in a closed container. It is in a closed container. Then only we can observe. So solid ice cube starts melting. But we also observe some of the liquid water is also churning into the So here what we are observing, solid water is changing into liquid water. Solid water is changing into liquid water. And again we are observing at the same time liquid water is also changing into the solid ice cube. So the rate at which the solid, three definitions I bring side by side. In this case, what did we observe? We observed a solid particle is changing into liquid particle, and at the same time the liquid molecules are converting into the solid ice cubes. This kind of system we are calling as a solid liquid equilibrium. What are we calling as, children? Solid liquid equilibrium. Do you remember our activity 1, something what we had learned in the previous case? What we had learned in the previous case, we have taken one container, and in the container we filled some water, and then after this water on heating, it changed into gaseous state, and some gaseous particles started condensing. So liquid water first changed into gaseous particle, and again these gaseous particles are touching to the surface of the liquid, they are again converting into liquid water. First case I am calling this one as a solid liquid equilibrium. What do I am calling this one as a solid liquid equilibrium. Second one I am going to call, the first one I am calling as a solid liquid equilibrium. Second one I am calling as a liquid gas equilibrium. What I am calling this one as the liquid gas equilibrium. One more example I take. We know camphor, children. Generally camphor will be in the solid state. If you take camphor in a closed container, you will observe this solid camphor will change into gaseous camphor. How do the solid camphor is converting into gaseous camphor? And later what do we observe? The amount of gaseous camphor that was changed is again converting into solid camphor. Means they are happening at the same speed. Means the amount of solid state of matter converting into gaseous state of matter is equal to the amount of gaseous state of matter converting into solid state of matter. So we say now the third type of equilibrium is observed under solid gas equilibrium. What is the third type of equilibrium we are seeing here? Solid gas equilibrium. How many types of equilibriums we got, children? Solid liquid equilibrium will be there, liquid gas equilibrium will be there, and also solid gas equilibrium will be there under the title called phase transformations or the physical equilibrium. Let us write definitions for all these, and we will copy it on the definitions also. So the points that we had learned now, we are writing in the form of definition, children. Write down the definitions here. The first one that we had learned now, the equilibrium in which the rate of melting of a solid, is equal to the rate of freezing of the liquid, is called solid liquid equilibrium. We had already seen the experiment. Now in a thermoflask we had taken some ice cubes and they were converting into liquid water, and the same speed the liquid water is changing into solid ice. So we observe up to 8 hours or 10 hours there is no change in the amount of ice cube in the thermoflask, not in normal condition, in which case in the thermoflask. So that's what we brought, is solid liquid are at the equilibrium states. And another example we started. We heated the water, we changed it to gas in a closed container, there the gas particles that are forming and the gas particles that are changing liquid are happening at the same speed. Further, this is the definition. The equilibrium in which the rate of vaporization is equal to the rate of condensation of vapor. The rate of condensation of vapor is called liquid vapor equilibrium. What is the third definition, children? The equilibrium in which the rate of vaporization of solid. We got camphor is changing into gaseous state and the gaseous camphor is changing into solid state. You can take even iodine. This is generally called as sublimation. Is it not? We learned in 9th standard. Now go to the definition there. The equilibrium in which the rate of vaporization of a solid is equal to rate of condensation of vapors into solid is called solid vapor equilibrium. So write down these definitions for the physical state of the equilibrium. Now we will see the dissolution of the solids or liquids in solutions. Now the next concept in the same is equilibrium involving dissolution of solid or liquid or gas in liquid solutions. What are we speaking about, children, now? We are speaking about this topic. What is the topic? Equilibrium involving dissolution of solid or gas in liquid solutions. A small experiment or small activity will take. Take one glass of water. What to take, some children? Some glass of water. In this glass of water, you are pouring some amount of water. So here we have the water. Right? I am calling this is our liquid. What I am calling this one as the liquid. Now in this glass of water, take 2 spoons of sugar. What you are going to take, children? 2 spoons of sugar. What you are adding, children? Sugar. 2 spoons of sugar. Sugar is a solid. Right. Very good. Now what do you observe? You are observing the sugar particles that are entering into this glass container. They are trying to dissolve or they are going to dissolve. Sugar molecules dissolves in liquid water. Is it not? So this process of dissolving sugar molecules into liquid water we are calling as a dissolution of solid in liquid. Dissolution of solid in liquid. What is our title? Equilibrium involving dissolution of solid or gas in liquid. Presently I am taking the solid in liquid. So what is the solid here? Solid is the sugar. Liquid is the water. What is then the word equilibrium here? Equilibrium means, for example, when we have added only 2 spoons of sugar, you can observe the sugar particles will be completely dissolving. 2 spoons will be completely dissolving. But you added the 3rd spoon. What you added, children? 3rd spoon. Once you add the 3rd spoon of sugar, first you added the 3rd spoon of sugar. What differences you will observe means some solid particles are trying to enter into the liquid water. But already in this liquid water some sugar particles are there. Sugar particles are there in this liquid water. Those sugar particles that are present in this liquid water, they will try to go and sit at the bottom of the container. What you are able to observe, children, now? When you had added the third spoon of sugar, some solid sugar particles are trying to enter into the liquid water. Some solid sugar particles are trying to dissolve in the liquid water. Parallelly from the water, some solid particles are settling at the bottom. We say the system has reached to the saturated level. What had the system reached to the saturated level? So at saturated level, the amount of sugar particles entering into liquid water were equal to the amount of sugar particles that are settling at bottom. Sugar particles settling at bottom of container. So we say the system achieved the equilibrium. So this is what about the dissolution of solid into liquid solution. Now let us see another example of dissolution of gas into liquid solution. What is another example, children? Dissolution of gas into liquid solution. Remember reading? Dissolution of gas into liquid solution. Dissolution of gas into liquid solution. Dissolution of gas into liquid solution. This is what our concept now. Do you know Sprite or Coca-Cola or Thumbs Up? Anything? Very good. Let us imagine there already in the bottle some water is there. In that they are filling some gas. How do they can fill this gas in the water? They must apply high pressure. Then the gas particles will try to dissolve into the liquid. This was first proposed by a scientist called Henry. Who proposed this one? Henry. What did Henry brought? He brought a law. He brought a law stating that the given mass of gas that dissolves in a given mass of solid is directly proportional to the pressure of the gas over the solution. Depends upon the pressure of the gas over the solution. The mass of gas dissolved in a given mass of liquid is directly proportional to the pressure of the gas above the solution. So in the containers generally we will see some gap will be there. Is it not the Coca-Cola or Sprite? In that gap what will be there? Pressure will be there over the solution or over the soft drink. So this was depending upon this topic. There is an equilibrium. Means what? The amount of gas particles entering into the solution, they are equal to the amount of gas particles that are leaving out of the solution. So they must be under at a constant pressure. They will fluctuate under the constant pressure. So in the next class we will see what are the necessary conditions for this equilibrium to be achieved. Thank you children. Have a nice day.